Hello everyone, this is the first time I go live on YouTube teaching the introductory concepts of waves or introductory concepts in waves. Hello and welcome. This video will cover the following concepts. First of all, we want to know what is a wave, that is the definition of a wave. We will look at characteristics which are common to all types of waves. Then we look at the relationship between some of those characteristics, that is the speed, the wavelength, and the frequency. And then we undertake a few calculations involving the above relationship, that is speed, wavelength, and frequency. And then I'll give you a takeaway on waves, including short notes on the waves, and there will also be an assignment. So stay tuned. This one will be available at the end of the video. In the video description, you will definitely get this package, but it is after we have gone through the lecture. So what is a wave? Now, before we look at what is a wave, I'd like you to bear in mind that anytime you are undertaking or you are in an online class, it's important to arm yourself with a notebook where you will be noting important points and going through the calculations together with me, because if you just watch what I do without engaging yourself in some form of activity, you won't get much. So there will be times I'll be pausing, asking you to respond to certain questions. So what is a wave? Simply put, a wave is any disturbance that transfers energy, or that transports energy, or a disturbance which moves energy. So energy has got a source of energy, and then once that energy has been converted from one form into the form which now can travel through this medium, a wave is created. Let's have a look at an example of such a situation, and we look at water waves. Here I've got a simulation. You can assume this one is a pond, and we are going to allow a single drop of water to fall into the pond. And that is what you'll get. You'll get a circular pattern that spreads from this point where the drop fell, and that pattern spreads throughout. If we had a light boat at some point here, we will be able to see that boat move up and down. That means that the water is disturbing it. But you also realize that the water does not undergo any net transfer. In other words, the particles of water at this point do not move all the way to where the boat is. It's only the energy that has moved. So water is made up of particles, and these particles are passing this energy in form of water waves from one particle to its neighbor. So all that the water particles are doing, they are moving up and down. That one is a simple example involving sound, involving water. Rather, we can have the same that involves sound. And if, for example, the drop were to fall on the pond continuously, you can see that circular waves are produced, concentric waves are produced, and they are moving away from the source. So this drop of water probably has got some potential energy. When it hits the water, that potential energy is converted into a form of energy which can move through the water, and we call that water waves. Now, we are looking at this pond from above. Let's look at it from the side and see what happens. Probably you have seen something like this in a swimming pool, where when you disturb the water at one end, there will be these waves which move from that point all the way to the other end. Of course, you can see that the height of the waves is decreasing. We are going to look at that later on and see what happens. So this one is something that you have definitely seen elsewhere or somewhere, and it is an example of a wave. Now, let's have a look at another situation here where I have sound waves. For example, this is a loudspeaker. Let me just, this is a loudspeaker, and when the diaphragm moves to and fro, you can see the diaphragm is moving to and fro. It is producing compressions. They are the white lines, and then the dark lines are the rarefactions. We will look at that when we look at sound as a form of energy, or sound waves, sound as a form of wave. So, but this one does not have any effect. Even if we were to look at it from the side, it just remains the same. It's not like water waves. How about light? Can we be able to produce the same effect with light? Of course we can. Over here, we are looking at a pulse, the way a pulse travels. When a single pulse is produced, that is what happens. We saw that with water waves. Again, we want to produce this light beam continuously and see what happens. Like that. Probably that one is a laser beam, and although we don't see it blinking, what happens is that light is a form of wave, or travels through air or through vacuum in form of a wave. So all these are types of waves. So what do waves have in common? So we have already said that a wave is a disturbance. This disturbance transports energy from one point, which is the source of the waves, to the surrounding region. A disturbance. But this disturbance does not move the particles of the medium permanently. What the particles of the medium do is to get energy from their neighbors, and then they transfer it to their next neighbors, like that. That way, energy moves along that particular path. It's more like in a classroom situation. If the student at the front of the classroom wanted to pass something to the student at the back of the classroom, all that he does is just to give the next student maybe that item. It could be a pen. Then that student gives the one behind. Then that one gives the one behind, until the pen reaches the student at the back. You see, the student in front did not move physically from the front all the way to the back. That will be permanent movement of the particles of the medium. Now, the pencil is, or the pen, or the item which is being transferred from the first student to the student at the back, is synonymous with energy. All what the students do, the students are like the particles of the medium. All that the students do is pass that pen from one student to the next until it gets to the back of the classroom. So it is important to understand that nature of waves, because all waves have got that nature. Waves consist of a disturbance. This disturbance transports energy. So disturbance and energy. Think about those when you think about waves. Now, let's look at a simple system that will help us to understand the characteristics of waves. And here, I'm going to look at waves on a rope. Imagine you're holding one side of the rope and you are moving it up and down. That is probably what you will see. You will see some up and down, some crest and troughs moving from where you are all the way to the end. You will see a wave profile actually move across the rope. But the particles of this rope, for example, let's look at this green particle here at the middle. You can see there is a green particle here. Let me see whether I'm able to slow motion. Yes, that is a slow motion. I want you to consider this particular particle. All it does is to move up and down about a certain mean position. This is the average or equilibrium position. And the particle is just moving up and down. All it does is that it picks energy from this particle and then passes it over to this other particle, and every particle behaves like that all the way until that energy reaches here. We can be able to look at this point here where the cursor is. You can see there is a crest. It's moving across like that all the way. You can imagine that to be the energy that is being transferred from one end to the other end. Now, these particles are undergoing a displacement which is perpendicular to the direction of travel of the wave. That by itself describes a transverse wave. I'll come to that later on. What I want you to observe is this. Let me freeze the wave so that we can look at the maximum displacement of this particle from equilibrium. And you can see it takes how many divisions? It takes 1, 2, probably 3 divisions, 0.6 centimeters. We can say that the amplitude of the wave is 3 centimeters. I've used a term here referred to as amplitude. So one of the characteristics of a wave is amplitude. What is amplitude? Amplitude is the maximum displacement of the particles of the medium from equilibrium position. Maximum displacement of the particles of the medium from equilibrium position or from the mean position. You might want to pause and write that one down. Amplitude is the maximum displacement of the particles of the medium from equilibrium position. Now, because it is some kind of distance, actually distance in a specified direction, it has the SI units, meters. So that is how we measure amplitude. We can also measure it from this other side, and you'll see it is the same. You can see from here 1, 2, 3 divisions, 0.6 centimeters. So you can be able to see that amplitude can either be positive or negative, but we always ignore the putting sign to the amplitude and just talk about the magnitude. It is the magnitude of the maximum displacement from equilibrium position. Now the next one is wavelength. And for us to be able to understand wavelength, we need to understand the meaning of a complete oscillation. Now over here, let me just remove everything. Over here, I have a simple pendulum. A simple pendulum consists of a mass, probably a bob, tied to a piece of thread, and then this mass is displaced through a small angle, like for example, that would be about 15 degrees, and then it is released. Let's see what will happen to it when it is released. First of all, I want it to oscillate normally the way we know it. That is how it oscillates. Now I want to slow it down so that we can see the meaning of a complete oscillation. Complete oscillation consists of a movement from here to here, which is the first quarter, and then the second quarter, then the third quarter, and then finally the final quarter. So a complete oscillation consists of movement from equilibrium position in one direction back to equilibrium position. The object bypasses the equilibrium position, moves in the opposite direction, and then finally comes to where it started from. That is a complete oscillation. A complete oscillation has 4 quarters. The first quarter is this one, second one is this one, third one is this one, fourth quarter, making a complete oscillation. Now, why do we need to study a complete oscillation? Let's go back to the wave that we had here. How would this complete oscillation look like? Maybe it is from some point here, it makes the first quarter, second quarter, third quarter, fourth quarter. That will be a complete oscillation when we are looking at the displacement position graph. Now, on the displacement position graph, the moment we are able to identify a complete oscillation, because you can even start from here, where I have this ruler, from here, this is the first quarter, second quarter, third quarter, fourth quarter, up to this point here. So this distance that the wave covers when it makes one complete oscillation is referred to as the wavelength of the wave. That is the second characteristics that waves have. Wavelength. Wavelength. Wavelength is the distance covered by the wave when the wave makes one complete oscillation. So on a wave profile like this, you could measure this distance from that point, all the way to this other point, about 1 to 3.8, for example, 3.8 centimeters. That will be a full wavelength. Or from this point here all the way to this other point here, again you can see it's approximately 3.8 from here all the way to this point, 3.8. So it could be from this point to this point, or from this point here, which is referred to as a crest, to the next crest. So that is how we define a wavelength. The distance covered by the wave when the wave makes one complete oscillation. It can also be defined in terms of phase, like this. It is the distance between any two particles on a wave which are in phase and they are following each other. What does it mean when we talk about particles which are in phase? Particles which are in phase have got the same displacement, the same magnitude of the displacement, and the same direction of the displacement. For example, this one has a displacement, maximum displacement, which we talked about, and we saw that it was actually 0.6. This one will be, 0.6 centimeters. So that is the maximum amplitude, and it is positive 6 centimeters. The other particles definitely have got a smaller magnitude of the displacement, but that magnitude of the displacement increases in the opposite direction, where we get another 0.6, but this one has got a negative sign. So they are not in phase. The next point which is in phase with this one is this one here. And you can see there is no other point other than this which is in phase with this one here. No other point. So you can see they are points which are in phase. And being in phase means they've got the same displacement from equilibrium position, or the same distance from equilibrium position, and moving in the same direction. It's like saying they've got the same displacement. So I've chosen points with maximum displacement. So this one has got a maximum displacement, and this one has a maximum displacement, and both of them are positive, and these points are consecutive. They are following each other. So that means that this is a wavelength. So a wavelength is the distance between any two points on a wave which are consecutive and they are in phase. We could also try to look at that definition from another angle. That is the distance between any two adjacent crests or any two adjacent troughs. This one is referred to as a crest, and this one is a crest, and they are adjacent. This is a trough, and this one here is a trough, and you can see they are adjacent. So Using that, you can be able to see that there are several ways that you can be able to determine the wavelength of a wave. And let's go to a simple exercise just to test whether you are following this. This one is a package that I have prepared for you. All you will need in order to access this document here is go to the video description. There will be a link for you to download that folder. Once you download the folder, you will find that in that folder there are very many files. You'll go to a file which is named index. Click on it and use your browser to open, because these are web pages. So you will open that folder, click on a file named index, and I would prefer if you use Chrome, because this material I've prepared it using Chrome. So go to that. As soon as you click on it, there will be this neat navigation on the left hand side here, and all you need to do is just click on that navigation. For example, Introduction to Waves. You can see over there, and there is a question here where I'm asking you, what is a wave? And probably if you are doing this all by yourself, I've given you some references there where you can be able to refer. You can be able to refer to this KLB Physics Students Book 1, page 170. If you read there, you will be able to get more information that helps you to answer these questions. Now, these questions are also on a PDF that I've provided you in the video description. Download that PDF and then print it out. That PDF has these questions. This is the way the PDF looks like. So when you open on it, when you open the PDF, you'll be able to see which form we are talking about. It's about review questions that are based on this particular lecture. You will go straight to the first part here. What is a wave? And then you can give me your answer. Maybe right now, just pause the video and try to answer that question. What is a wave? Now, after you have answered that, you go to the next one. What is meant by amplitude? What is meant by wavelength? Answer all those. Now, once you have answered those questions, I'm just trying to show you how the two packages work. You'll now come to this web page here. What is a wave? You're reading here, and if you want to know the answer, just immediately, just click here where it is written, click here to see the answer. And let's see what happens. When you click on it, there is a lot of information on what you can be able to write down. And probably the one that I expect is a wave is a disturbance which moves or transports energy from one point, which is referred to as the source of energy or the source of the disturbance, to the surroundings. That would be enough for that particular space. I've given you a few illustrations here testing that question. I mean, explaining further on what a wave is all about. Now, once you've read that and maybe you never got it correct in your answering on the PDF, you will hide it and then you go back to the PDF. You will go back to the PDF, erase whatever answer you had written here, and now write it correctly. Now, why is that important? Why is it that I want you to be able to write down the answer before you can check what the correct answer is? This one is so important because if you don't follow it, it means that some of the materials you will think that you have understood, but actually you've not understood anything. So we learn best by repetition. So having explained how this one is done, and remember, you have to print this PDF. You have to print it, answer the questions. You can give it to your teacher to mark for you, or you can just use these web pages here to assist in the marking over here. Even when you go to let me see about characteristics of waves. When you go to characteristics of waves, and the first characteristics is amplitude. I've asked you to define the term amplitude as used in the study of waves. Again, you go through the process of answering that, and once you click there, you'll be able to see the answer. So that is the takeaway that you get from this video. However, let's continue and look at other characteristics, which are frequency and the speed of the wave. So while we are here, we can be able to measure, for the simple pendulum, we are actually able to measure this time here, the time for one complete oscillation, which again starts from there at the first quarter, the second quarter, the third quarter, and of course the fourth quarter. That time, how do we measure it? So we need a stop clock or a stopwatch, rather. Here it is, and I wanted to measure the time for one complete oscillation. So let's start from some point there, and I'm going to set it in motion, and then also start the stop clock. First quarter, second quarter, and then the third quarter, and then when we are at the fourth quarter there, I stop the stop clock, and that tells me that the time for taken by this bulb to make one complete oscillation is 1.96 seconds. That is the periodic time. So periodic time is the third characteristic of waves. The third characteristic of waves. Periodic time is the time taken by the wave to make one complete oscillation. The time taken by the wave to make one complete oscillation. You might want to note that one down. Time taken by the wave to make one complete oscillation or one complete vibration, something like that. The SI unit of periodic time is, of course, seconds. Now let's look at the fourth characteristic, which is frequency. Frequency. So in 1 second, how many oscillations does this pendulum make? Now I've gone back to the normal situation where we've got the pendulum, and this is the way it swings. In 1 second, how how many oscillations does that bulb make? So the number of oscillations that the wave makes in unit time is referred to as the frequency of the wave. Maybe it makes 5 oscillations in 1 second. So the frequency of that wave will be 5 oscillations per second, and an oscillation per second or a repetition per second is synonymous with an oscillation. So the words such as how many crests per second, how many vibrations per second, how many repetitions per second, we are just describing frequency. Frequency is the number of oscillations made in unit time. So write that one down. Frequency is the number of oscillations made in unit time. The SI unit of frequency is Hertz. Hertz. H-E-R-T-Z. H-E-R-T-Z. In short form, that will be capital H and small letter Z. Hertz. Let me just illustrate this so that you can be able to understand further and be able to get the concept clearly. So far, this is what we've been able to see, that there is a wave that you can be able to draw here. So it will be vertical displacement. And this is what we are able to see. Able to see that kind of wave like that. And if this is the position or horizontal distance in meters, for example, and this is the vertical displacement S in meters again, you can see that this is the maximum displacement of the particle from equilibrium position, and we referred to that as the amplitude. And then this is a complete oscillation. So that distance from one crest to the next is wavelength. Now, if this same wave was such that we are drawing a displacement time graph, displacement again in meters, and here time in seconds, and maybe the kind of wave we get this time is something like this. You can draw a better one in your notebook. Now, this is a crest and this is the next crest. This time here, remember it's no longer distance because what I have on the x-axis is time. So it is not distance like the previous one. It is time. So this time taken by the wave to make one complete oscillation is what we are calling periodic time. Periodic time. And let's assume that maybe this is 1, 2, 3, and then somewhere here. Let's assume that this is 1 second. Let's just assume it is 1 second. From here to here, it's 1 second. Let's count the number of oscillations that have been made in 1 second. So it will be 1, 2, 3 and a half. So the frequency definitely is 3.5 Hz. So this wave makes 3.5 oscillations in 1 second. So the frequency is 3.5 Hz. Now there is a relationship between frequency and periodic time. There is actually that relationship because this one is a period, this is another one, this is another one, and this is half a period. So we are going to see, since this from here to here is t plus another t, that is 2t, plus another t, that is 3t and a half. So we have 3.5 t in 1 second. So once we make t to be the subject, we're going to divide that one by 3.5. And what is 3.5? 3.5 is the frequency. It is the number of oscillations made in 1 second. So we're going to say that this one is 1 over f. And you get a very important relationship where we say t is equals to 1 over f. So Hz frequency. So you can see we've been able to define all the 4 characteristics of waves. The first one was amplitude, maximum displacement of the particle from equilibrium position. The next one is wavelength, which is the distance covered by the wave when the wave makes one complete oscillation. The third one is periodic time, which is the time taken by the wave to make one complete oscillation. And finally, we have frequency, which is the number of oscillations per unit time or made in unit time. And the SI unit of frequency is Hz, Hz. Now, don't be confused by these fractions. And when we are defining frequency, avoid saying that it is the number of complete oscillations made in 1 second. That is wrong, because it can have a fraction of an oscillation. Like here, I've deliberately ended this at 3.5 so that I can show you that the frequency, the number of oscillations made, they need not be complete, numbers. They may have fractions of an oscillation. Now let us go ahead and look at another characteristics which is referred to as the speed of the wave. The speed of the wave. Now, let me get that one traveling. And probably I'm going to look at this point when it is here, when there is that crest, travels like that, all the way until it comes to some point here. So I might want to measure this distance from that point all the way to some other point here. So you can see that this wave profile is traveling like that. We can make it move faster by changing the nature of the medium through which it is traveling, but I'm going to maybe increase the frequency. Let's see what happens when I increase the frequency. So this one is now higher frequency. Yeah. So we have that crest which is moving like that along the Kcse, like that. So that the distance covered by this wave in unit time is what we refer to as the speed of the wave. So we will measure the distance that the wave covers all the way from there, all the way, follow that crest until maybe it covers 5. Measure that time, and you can see we've got a timer here which can help us to do that. When we divide that distance by the time it takes to cover that distance, we will get speed. So, speed of a wave, V is given by distance over time. And you can see since distance is in meters, time is in seconds, then the units are meters per second. Meters per second. Now, for one oscillation, the speed can be calculated by dividing the distance covered by the wave when the wave makes one oscillation. The distance covered by the wave when the wave makes one oscillation. That is wavelength. And divide it by the time it takes to make one oscillation. And that is periodic time. So I can separate these two, lambda times 1 over t. And we have just seen that 1 over t is frequency. So you're going to have lambda times frequency. So speed of a wave is equals to, actually, let me start with the frequency, then multiply it by lambda, like that. And that is the point that I wanted to stop in this particular video, where we are looking at the introduction parts to waves. Now let's do one simple calculation so as to see whether we have understood this concept or not. So let me go to frequency. Of course, once you get this, you can be able to reflect on what we learned. I don't want to go through that right now. Even for speed of a wave, just to define what speed of a wave is expected there. The equation that governs speed, wavelength, and frequency, we have just talked about it. So once you click here, you'll be able to see speed is equals to wavelength times frequency, and in short form, it is like that. Now let's have a look at just a few examples. There is an example here that I've given where we have waves on a spring are produced at a rate of 20 wavelengths every 5 seconds. 20 wavelengths every 5 seconds. Find the frequency of the wave motion. Let's do that and see what we get. So I'm going to keep the question there as I write down here. So this is it, 20 wavelengths every second. Frequency is the number of oscillations. That number of oscillations divided by the time taken to make those oscillations. A wavelength is a complete oscillation. Just remember it from here. You can see a wavelength is a complete oscillation. And here we are being told that it makes 20 wavelengths every 5 seconds. So we are going to divide the number of oscillations by the time, and we get 4 Hz. B. In part B, if the wavelength of the waves is 0.01 meters, find the speed of the waves. So speed is going to be equal to frequency, which we have worked out, times the wavelength. The frequency is 4 Hz, or 4 per second, times the wavelength, which is 0.01 meters, and I get 0.04 meters per second. Very easy. And then finally, find the period of the waves. C. The period, which is T, is the inverse of the frequency. Again, we have just derived that here. We have just derived it, so it's not such a big problem. So we are going to have 1 over 4, which gives us 0.25. What are the units? Seconds. Now, once you go through this in the assignment that you have already printed out, because like you can see, that question is here in the assignment. It is here. So once you print it out, do that particular question all the way to the end. You can also do the other one over there. There are several of them that I've given. Once you have done all these, then you will go back to this product here, or to this package here, or to these web pages. Then click to see whether the answers are correct. And you find that there will be some answers that I've already provided you with that you can use to mark your work. So make sure you go to the video description, download the assignment PDF, download this folder, use the instructions that I've given you to answer those, to get this. Use the instructions that I've given you to open the correct file. Remember, the correct file is index, and you open it using a web browser such as Chrome. Microsoft Edge will also do, Firefox will do, but I would prefer you use Chrome. And that is all we had time for in this particular lecture that covers the whole topic on Waves 1. Now it's up to you to do the assignments, to go through that these packages, these web pages, and see whether they are helping you. The trick is, once you get the answer wrong, hide the answers and then go back and redo it once again. Again, come and click here to find whether you're getting the answers correct. So I'm planning to have a series of live YouTube lectures where you can ask me direct questions. This is the first one, and of course the others I'll be notifying you when we are going live. So if you have not subscribed to my channel yet, so that you can be informed when I'm going live, do that immediately, so that when I'm just about to go live, you are there and you can ask me questions directly. Otherwise, until that time, goodbye.